So today we will be covering Perceptron, one of the basic and the most fundamental algorithms of neural network. Now, in machine learning, this perceptron is basically a supervised learning technique and a binary classifier. In other words, it is basically a linear classifier. That means it can classify the inputs by drawing a linear line into your 2D plane so that it can classify your inputs into two categories, yes or no, say for example, 1 or 0. So this algorithm actually allows for the online learning mode. Online learning mode means that the moment more and more input comes in, it can keep on incrementing its learning. It can you can add the inputs as they are prepared. So it can allow the inputs at a dynamic time also. So that is why this word online learning has been added here. The Perceptron algorithm is not a new algorithm. It dates back in 1950s, where the first implementation came in the form of a custom hardware, and it is considered to be one of the first artificial neural network to be produced. So let us look the basic architecture of this network. As you can see, we have the inputs. These X are all inputs, and we have the corresponding weights associated with these inputs. And we can also have the bias weight if required. We can have the bias weight where the input, as you know, would be your unit weight, unit value, and the weights, it can have some kind of weight also. The basic the activation function which is used in Perceptron is pretty simple. As you can see that it can produce the output as either 1 or either 0, right? So 1, it can be the case where this summation is greater than equal to some threshold value theta. Or otherwise, if this value is less than theta, then it can produce the value 0. Right? So we can rewrite this equation, above equation, this form, right? So it takes the input, aggregates, and returns 1 if the aggregate sum is more than some threshold value. Otherwise, it will return what value 0. Right. So this is what I was talking about. If in case we wish like to add the bias weight, then this can be represented in this fashion. Right. So this is another way of representing the same equation we did earlier. But this time we have taken the summation from I is equal to 0 in order to incorporate this additional bias weight. So a single perceptron can be used to implement a linearly separable function. Linearly separable, as I've told, we can separate the inputs given to us in a 2D plane by drawing a linear line. Right? So it takes both your real as well as the Boolean inputs and associates a set of weights along with them, a bias value also. So this is what this activation function can be represented in a simple manner, which includes the bias value also, and these are your weights, and this is your input, right? And as you all know that this bias value, I'm talking about this bias value, this bias actually does what? It basically shifts the decision boundary away from your origin, and it does not depend on any input value. That is why it has been taken separately. Now this value of fx, that is the activation function, which can be either 0 or 1, it is used to classify x as either positive value or a negative value, right? A negative instance. Mostly in most of the cases we see that neuron does two kind of jobs. Either it excites, that is it fires in terms of giving the value 1, or either it inhibits its input by producing the value of 0. Now, if this bias value B is negative, then the weighted combination of the input must produce what? A positive value greater than this bias in order to push the classified neuron over 0 threshold. And practically, it has been found that this bias alters the position of the decision boundary, as I have already made it clear. And this perceptron learning network actually does not terminate if the learning set is not linearly separable, because this algorithm is only made for separating the inputs in a linear manner. So if the inputs are not linearly separable, the perceptron would fail. So we would do an example of XOR to see that if the inputs are not linearly separable, then this algorithm will not work. And the most famous example of this is your XOR, which I was talking. As you can see that being an online learning algorithm, so this separator or the separating line needs to be adjusted so that you can classify inputs, and the inputs can come at a random time. It can come at dynamic time. So the inputs keep on coming, and we need to just keep on shifting this separate or this linear line. So this line gets adjusted the moment some input comes in. So this algorithm is basically a kind of online learning algorithm. Now, in the context of this neural network, a perceptron can be thought of as a Hippiside step function, which has three range of values. One is 1, either it can produce the value -1, or either it can produce the value 0. The perceptron algorithm is basically termed as a single layer perceptron, having only a single layer of a neuron, right? So if in case we have multiple layers of neuron, then it becomes a multi-layered perceptron. So this is how we distinguish between single layer and multi-layer perceptron. And as a linear classifier, the single layer perceptron is the simplest feed-forward neural network. So let's do an example, understand that how the training can be done and what are the important aspects of it. So this is what I was talking about, that we can use a Heaviside function where we have three ranges of value. This is your output. So we're talking about the activation function, which can produce a value of 1 if your total activation input is what? Y in, right? So the Y in is greater than 0, then we can produce a value what? We can produce a value of 1. If in case the Y in is 0, then we can produce a value 0. If in case the Y, that is the total activation input, is less than 1, then we can consider that output is -1. So this is what we would be using this activation function to explain an example. So if the output is erroneous, the concept is that once you produce an output, so we just compare this output with the expected output or the target value. And if there is some error, then we would be adjusting our weights. Then we would be finding the adjusted weights. Otherwise, the interconnection weights would be left unchanged. So this is the basic funda or the rule that we are going to use in this particular algorithm, which can be represented in the form of statements like this. If the Y output, that is the calculated output, is not equal to your target, right? Then what we are going to do is, then for all the corresponding weights, we would be finding the new weights. We would be adjusting the weight function, right? So new weight would be calculated by a formula like the new weight is nothing but is equal to the old weight, and plus we have this weight updation rule, which includes your learning parameter, right? This can any value between 0 and 1. Then we have your target value, and then we have your what? Your input value. So these are the factors that would be calculated in order to find your new weights. Or else, in another case, if this Y output, that is the calculated output in every iteration, becomes equal to your target value, in that case we would initialize, or we would equate the new weights with the old weights. There would be no change. There would be no calculation of your weight updation rule, right? So this is a basic fundamental algorithm that we would be using. Like as we all know that step 1 or the initial step talks about the initialization of weights, right? Either the weights would be given or it can be initialized. So we would be initializing the weights and we would be initializing the bias. For simplicity in our example, we would be taking all of these values to be 0. And then we can have a learning rate, which also gets initialized between the value of 0 and 1. So this step 2 says that step 2 basically involves a loop, which will continue till we reach a stage where all the inputs, all the calculated outputs, all the calculated outputs become equal to the corresponding targets, right? And each of the iteration, what we would be doing is we would be setting the inputs, right? And then we would be computing the activation input here, and then we would be applying the activation functions in order to calculate the output. So let's see one example here. And step 6 would be the way I've already made it very clear that we would be In case the target is not equal to your calculated output, then we would be updating the weights. Otherwise, the weights and the bias will remain same. And this would continue till the case where all your calculated outputs are equal to the target values. That is, in that case, we would say that a convergence has reached. So we'll take this example where the concept is that we want to make a perceptron model or network for realization of your end function with two inputs. So here we will have a bipolar inputs and targets, right? And the function is what? End function. So as you know, the truth table. So this is the truth table that we have developed, where we have bias value, as you all know, all are dummy inputs, and we take them as value 1. And these are the corresponding targets that we want our network to get trained. So let's run the algorithm then. Step 1, we need to initialize our weights and bias. So for simplicity, what we have done is we have initialized our weight, because we have two inputs, so there would be two corresponding weight values, right? So both the weight values have been initialized to 0, and the bias value has also been initialized to 0. Again, for simplicity, just for the explanation part, what we have done is we have taken the learning rate to be 1, right? But ideally, learning rates are never 1, right? And then we have taken the threshold value to be 0, right? So the first step, what we need to is we have to take one inputs one by one, and then we need to calculate the output, and then we'll see that if it is equal to target, then we are not going to make any changes. Otherwise, if it is not equal to target, then we would be updating the weights, right? So for the first corresponding input, that is the first input, let us see what has to be done. So the first corresponding to the first input, then we need to first calculate what the activation input. So the activation input would be applied by this formula, as we all know. So since the bias value was 0, since your weights was 0, so the entire term would be over here would be 0, right? So as per the activation function that we have developed, so this comes out to be this condition in this case, right? Because the total activation input yn is what? 0. So if it is 0, which satisfies this part, so the total output value in this case would be 0. So therefore the y becomes what? 0 for the input 1, 1, right? So in this case, since the target was 1, since in this case 1, 1, the target was 1, and the corresponding calculated output we have calculated so far is what? 0. So both becomes mismatch. So as per the rule, when we said that if the target and output is not same, then we have to find the new weights, right? So the new weight calculation formula was like defined like this. So for the finding the new weights for, so what we have to do is we have to find both the new weights, that is W1 and W2. Both the new weights have to be calculated. So it is based on what? The old weight plus the factor which involves your learning rate, which involves a target value, and which involves your input value. So W1 new become what? W1 old. W1 old was what? Value 0, because we have initialized every value with 0 value. And then alpha we have taken 1. Then target value over here was 1, and the input over here was 1, right? So what we get is 1. So the new weight over here is weight, and similarly W2 would be calculated, which also comes out to be value 1. And the this bias value, the new bias value would again be calculated, the old value plus alpha t. Why x is missing? Because we all know that for bias we take the input as 1, right? Only the weight value gets updated. So in all, the bias value also becomes 1. So after the first iteration, what we get is now this 1, 1, 1 is what? This becomes your W1, new W1. This becomes your W2, right? And this becomes your W0. So this is what we have got from after the first iteration of training. So let's move on to the second input now. So what we have done is we have initialized this table now. So we have done with this input, right? So we have done with this input, and that is what we have obtained. So this is the condition that we have reached and have explained just now, right? So again, what we'll do, we'll take the second input, that is -1 and 1. Bias would again be 1, right? So in this case, if we are going to follow the same scheme that we done, we did earlier. So we would be calculating the net input, which comes out to be 1. Then based on the activation function rule that we defined, the output would be 1. And the target over here is -1. So again, since the output and the target value varies, so it is not same, we would be doing what? We would be calculating the new weights, right? So for calculating the new weights, what we have to do is, this is the change in weight. So we would first calculate the change in weight for W1, W2 as well as for your bias value. So the weight change formula is what? It involves alpha T into Xi, right? And when we would be calculating the new weights, then we have to add up the old weights along with the value of del W in order to obtain the new weights, right? So since over here alpha was 1, right? T was what? Target value is what? Target value is -1. And your x1 is what? X1 is, over here is -1. So -1 into -1 will produce a value of 1, right? I hope that is clear. And similarly, in same sense, del W2 involves what? It would involve again alpha. It would involve your target. Target is again 1. And it would involve your value input x2. So x2 is positive over here. So x2, that is 1 into -1 would produce a value -1. So I hope that is clear. It's a pretty simple calculations. And similarly, you can calculate a del B also, right? So after doing so, how this value 2 came? This value 2 came because the old weight. So mind you that we would not take now the first, because that was the initial part only. So the new weights at this point of time, the current weights are W1 is 1, W2 is 1, and W2 this and del B W1 is 1, W2 is 1, and your B is also 1, right? So what we are going to do is the change in weight at this point of time, we got what 1. So this one would be added with your old weight. Old weight is at this point of time would be considered this value, not this value, right? So this 1 plus of 1 would make you 2, right? Similarly, when we would be calculating for this case, that is W2 new weight. So W2 would be calculated in what form? 0 comes from where? This -1 plus of your old weight, that is 1, right? And similarly, this would be what? Your -1 plus of this value. So again, it would be 0. So I hope that is calculation is clear now. So so now this 200 becomes your current updated weight. So when we would be doing the further iteration, for example, when we come up with the new input 1 and -1, so the change in weight comes out to be -1, 1, and -1. So how this weight would come? We would add this 2 with -1, which comes out to be 1. Similarly, 0 with this, and similarly 0 with this value, right? So this is how we update the weights. So after presenting all the inputs, so we had what 4 inputs, right? So after presenting all the possible kind of inputs, so the final weights that we achieved was this one, right? So we had what? W1 is 1, W2 is 1, and B is what? -1. So this is after presenting all the inputs. So when we say that we have presented all the inputs, we often say that we have done with epoch 1, right? So we are done with epoch 1. Now, as you can see that we have to check that whether we have achieved the convergence or not, right? We have to see that whether we have achieved the convergence or not. So before that, let us also understand that what this weight means. So what we have done is W1 is 1, W2 is 1, and B is -1. So what does imply? So it basically implies a equation of line. So this weights basically applies what, or it signifies that we can draw a line with this present values of weight after epoch 1. So how do we do that? For doing so, what we have to do is we have to equate this term to 0, right? In order to draw a line, what we have to do is we have to equate this term to 0, and then we will calculate the x2 out of this entire one. And then in this case, what we will be doing is this formula. We will be putting this value of W1, W2, and B, and then we would be obtaining a line of equation like this. I hope that is pretty simple. You would be putting W1, you would be putting W2, you would be putting B, and you would be putting what? W2. So after calculation of this, so what we would be getting a equation of line like this. So this is what we have got over here. So once we get this equation, we can definitely draw a line in a 2D plane where x1 is on the x-axis and x2 is on the y-axis, right? So this line basically signifies the what is the learning or how the network have learned after epoch 1, right? Now the thing is we have to decide whether we have whether we have achieved the convergence or not. Actually, we have not achieved the convergence, and for that, how we are going to verify that whether we have achieved the convergence or not? By looking at this two values, that is the calculated output and the target value which was already given. So we can see that we would say that the convergence has achieved where a condition reaches where the all the output values, that is all the four output calculated values, become exactly same as your target values, which is missing over here. So the iteration 2 would begin, or the epoch 2 would begin, where what we would be doing is we would now take the W1, W2, and B as these weights, right, rather than 0, 0, 0. And the same procedure would be repeated. Again, the same set of all the inputs would be given, right? Again, the same kind of algorithm would be applied, and then this would continue till a stage where all your target values become equal to your calculated values. And once we achieve that, then so in every iteration or in every epoch, what we would be doing is we would be drawing one such line, right? And once a stage is reached where we say that the convergence is reached, then that line in the final round would be confirmed as your final separating line, and that would ideally should be able to classify your inputs into two regions. Say here the classification was what? Here we had what two kind of inputs, right? One was what? If we can see that this is basically was an end function. So what was right? What was done? Like for these kind of inputs, so there would be one class which corresponds to 1 1, which is what 1. So this is one kind of class, and rest there would be another class which we can call it what another class -1 or 0 whatsoever. So basically this was a linear classification problem where we had two kind of classes in which we have to classify, or which under which we have to classify all our inputs. So that is what we are talking about. So for example, this could be the case where the class 1 can be represented by plus, and the rest all the -1 could be represented by these dots. So this is what we are doing, or that is what we do with perceptron models. The same manner we can do or build a network for OR function. Now, it has been observed that, so this is what I was talking about. So this is an example of OR function where it takes two epochs. Like for example, if you would look over here, so in the first epoch, after first epoch, what we get is the this calculated output value and target value. We can see that these for all the values it is not same. So we would go for epoch 2, right? And epoch 2, what we find that over here after epoch 2, we can see that all the target values are now equal with your output values, and this is the end of your iteration. And after the end of the iteration, the weights that we would achieve or would gain, that is W1, W2, and your bias value, this is would be your final weights, and corresponding to which we would be drawing some line which would be the final line of convergence, right? So I hope we would be able to develop small such kind of networks, right? So this is another example where we had only what two inputs, right, in the previous examples. So we can have any kind of inputs, any number of inputs. Over here, what we have, what four kind of inputs: x1, x2, x3, x4, right? Again, the inputs are bipolar and your bias value. So again, over here, the for corresponding target, what we have done is these corresponding targets already given. So we would have been calculating your corresponding output values, and then we would be waiting for a phase to come where all your target values become equal to your calculated output values. So over here, this is after epoch 3, we achieve this particular case. So this the final output value, that is 0, 2, 0, would be termed as your final convergence line, right? Corresponding to which there would be one separating line. So this is what Perceptron algorithm does, and this Perceptron learning algorithm, when we consider it for a higher degree of layers, that which also includes your hidden layer, then it becomes what? A multi-layer perceptron model, right? Which one of the basic algorithms of which is your back propagation learning algorithm, right? So this is all about this perceptron neural network. Thank you.